So I have cut the trace files. The original trace file has all the execution, has the initialization phase, all the iterative behavior. I have cut the trace file to work with few iterations. This is a typical approach we use, is that instead of working with a full trace file, we first have a look on the full execution, and then we identify what we call a region of interest and focus our study on this region of interest. Okay? So I have loaded the trace file in memory. The tool by default do not display any window. Okay, this is the main screen of Paraver. And then what I do is, one thing I want to mention is the tutorials. I will show you that on the hands-on to do it by yourself. But basically, you go to Help and Tutorials, and you get a list of tutorials you can apply. Okay, as I said, number 1 and 3 are the good ones to start. And I will start with number 3 just to get some easy way of the configurations I want to use. So you can go through it, you can read the tutorial, and you get insight on how to interpret the data you get. Okay? But basically, when you identify a link, you can click on it, and it will open a view. Okay? This is the profile of the MPI calls. Okay? So here I automatically have my profile, and here I see this 95% efficiency. So the numbers, very similar numbers to the ones I provided on the slide. Okay, so I see my efficiency is very good. I see some small component for the communication and also some small component for the load balance. I can open the timeline, okay, and I see a long time. I see kind of 2 iterations. I see if I put on top of a color, I see what it means. This is an all reduce. In fact, the application is doing an all reduce. Only for each process, so it's not a real communication. It's just a kind of local all reduce, okay? And this is the communication phase where you have I send, I receive, and waits. Okay, sorry, I forgot. If you eliminate the colors here, you will see this is I send, I receive, and waits, and the all reduce, okay? So I can zoom in and see the communication. I can always right mouse button will show you the options you can apply. You can view the communication lines, okay, and you can see the communication pattern. You can see, sorry, I take me out. You can see some large MPI wait calls. You can see that now here the communications get better balance, not so much waiting. So you can try to understand why this happened. So I can zoom XY just with the control drag and move button. You can try to understand why this large wait happened. Okay, so this is the processes. These are doing computations and the local all reduces, and this process is computing until this time. Okay, so it seems to create some waiting time with other processes. We can check with the hints. Sorry, let me try to do it better. The hints is a new functionality we have developed in Paraver that allow you to identify for a given trace file the kind of information you can process. So when you load the trace file now with the new versions of Paraver, this trace file is telling me it has MPI information, it has callers information, it has hardware counters, and it has flush. Okay, so it's the kind of information I have. And then the hints menu told me some recommendation of views I can do for these different things. For instance, for MPI, I can compute the connectivity pattern, okay? So automatically computes for me the table, what is say each process to which process communicate. So I can see basically one process is communicating with the partners on the 2 sides, rank -1 and +1, okay? So this process is communicating, is computing, this is unbalanced, so this is doing computation, so until it reaches the phase of communications, the neighborhoods have to wait for him, okay? But what happens, this neighborhood have to wait for him, but then the next one has to wait for the previous one, so there is a chain, a bubble that is creating for waiting time because one of the processes were delayed, okay? So if we unzoom, we see back to all the processes. Let me take out the communications lines, okay? So you see this kind of bubble, so this process is taking more time, and going up and down, you get this bubble of waiting time, okay? The same happens, this process is taking more time for the computation, so it has to communicate with the one after it and with the one before. So it's the bubble they're going down and up. Okay. So all these large MPI weights calls is caused because imbalance between the processes. Okay, and it is distributed over the serialization chain to all the processes around. Okay. Once all these bubbles are absorbed because the communications take place, you have this communication pattern. Okay, you can use the lines here, where it's very clean. You can see each process is communicating with the neighborhood very clean and very smoothly without waiting time. Okay, so this means that if there was no imbalance, with zero imbalance, all the communication pattern will be like that. Okay. But with the real imbalance, you have this behavior, okay? So we have seen some reasons for imbalance. We have seen the communication effect, okay? So if you remember, the efficiency was good, but there was some problems of communications and dependencies, and the reason is this imbalance is producing this large waiting time. If we want to look at the computations, okay, as the second component, I can go to the tutorial and click on the second button. This is a histogram of the duration of the computing phases, okay? Because what I have seen here is that in many applications you have large computing phases and then the communication phase. But here the granularity is small. If I put my mouse on top of it, I see the number here saying this is the average duration of this computing phase, okay? So it's 1 millisecond, 1.8 millisecond. Sorry, I didn't want to do that. So what I see is, as I said before, darker means more important. I see some variability, some small variability. Let's say it's not not vertical line, but it's neither a clean vertical line. Okay, so there is some variability for the different processes. And within the same process, there are variability in the durations. Okay, I can see where did this happen on the timeline, just clicking on this button, and I'm now only focusing on this large duration phase. I can fit the coloring for this value. Okay, and I see kind of a random durations, the smaller and the darker. Okay, so this is not a structure. So basically, my computation is this length and is small computing phases one after the other that are separated by this all reduced call that is only local for the process. Okay, so it's not a real communication phase, but it's a local communication. So I can look at the number of instructions. So with the hints of hardware counters, the histogram of useful instructions. Okay, and I see seems initially more vertical line. I can zoom in. Okay, and I also see variability. Okay, if you compare these two shapes, you will see they are almost the same. Okay, being so similar means that there is a correlation, there is a high correlation between the number of instructions and the duration. Okay, so variability on the duration, is caused by variability on the number of instructions. Another way to look at that is I can take this picture and I can correlate it directly. So what I can do is I select to correlate with metrics. So now I'm correlated with the IPC. It's here, instructions per cycle. So I can see, in average, this is going 1.4 IPC. That I think it seems to me is good for Pi, at least with the two codes I have executed, is one of the higher values I obtain. I can zoom on this region, okay, and now I see the correlation. Now the coloring means the IPC I get, okay, and the position in the plot means the duration, okay. So what I see is that, is going from darker to lighter, meaning that when I'm becoming larger in duration, I'm getting less IPC, okay? It's a clear correlation because as much as I move to the right, as lighter I get, okay? This meaning that as much time I get, less IPC I get, okay? So is this correlation that IPC is affecting to my duration? Okay, if I correlate with the number of instructions, okay, it's a gradient. Now it's the other way around because When I take more time, it's because I'm doing more instructions, okay? You see this correlation going from lighter to darker, meaning this is a correlated metric, okay? If you don't see a correlated metric, this will be kind of a randomness where you get darker and lighter on any place, okay? There is a correlation because the gradient is on the same shape than the table, okay? So, and if I go back to, the IPC, I can see the IPC of this region is going from 1.47 to 1.36, okay? So this is the variability on the range of IPC. So, as I said, these IPCs are good. There is this small imbalance. But in fact, this small imbalance within this region is not the real problem. The real problem is that some processes do more chops than others, okay? So this phase is just a small region here, okay? So you can see this is a sequence of this region is one. Let me open. I think I have opened already. If I can synchronize two views, so now they will move on the same scale. Okay. So I can fit the coloring. Okay. So if I zoom here, I see this 1, 2, 3, 4 iterations, 1, 2, 3, 4 iterations. Okay. So basically this granularity is a small chop. And what happens is that there are some processes that get more chops than others. Okay. Maybe it's easier to look at it that way. Okay. So you see, this process finishes the number of chops. The chops, there is some variability on the chops that is kind of randomness between processes and a long time. But then there are some processes that finish the chops here, while others still have to do some other chops region they have to do. Okay? And this is the reason of the imbalance. So the real imbalance is because the number of chops each process is different. Okay? And this imbalance is the one that causes this waiting time. So I think we have a little bit understood the performance of this execution. So now we can compare when we double the number of processes. So I load the trace file with the double of processes. And I can start using the load previous configurations. Show me the previous files I have loaded, the previous view I have loaded, so I can use that to easily load the same views on the new trace file. Okay. So I will start with the profile of MPI. Okay. I can scroll down, take out the coloring here, and I can compare with the profile on the previous execution. Okay. So looking at the numbers, power efficiency goes down from 94 to 90. Okay. The communications 97, 94, and the load balance 97, 96. Okay. So I see the load balance is quite similar, and there is a little bit more penalty on the communication. Okay. So I can compare the executions. Oh, sorry. Let me unsync the views. Take out that one. I can copy from here and paste. I have a copy. Paste the time, so they show the same time interval, okay? And what you see is that basically I double the number of processes, and now I take close to half the time, okay? So the scalability of the code is good, okay, because it's almost half of the time, okay? And what you also see is that in this, with 16 processes, the region has 2 communication phases, but the equivalent region with 32 processes have 4 communication phases, okay? I can draw here also the communications. And if we have a look on one communication phase for each of them, okay, this is the one we had said before. This is the one here now, okay. Again, maybe it's better I take out the communications to see the behavior, but it's the same shape. This process is taking more time, So these other processes have to wait for him, and the bubble is going down and up. Okay. This process here is also taking more time, so again it produces bubbles. Okay. So this waiting time is distributed for the processes through this chain of communication. I can check, but basically the communication pattern is the same. You communicate with your closest neighborhood, and this variability on the number of chunks you have to process produce this waiting time at the beginning of the communication phase. In this case, in fact, the communications are finished and the bubbles were still being absorbed by the pattern of communication. Okay? So we can compare also the computing phases. Okay? So we see there is variability, but there is a similar behavior with respect to this imbalance and this communication waiting time in the MPI wait. So if we compare with respect to the computations, we can go to previous configuration and load the useful duration. Okay, so I got this one is for the new trace file. I open the same one. You don't have to be scared with Paraver. You will finish opening many windows, but that's fun. So I open the same one, and in fact I can copy and paste the control scale. So they show the same dimension for this table. Okay. And they show the same structure. So let me put percentage of time. Okay. So what I see is I compare the duration of the computing phases with 32 processes and 16 processes, and they are very similar. Okay. So this is showing the granularity of the computing phases. So meaning when I double the number of processes, the duration of my computing phase is the same. Okay. It's just the number of computing phases that is modified, okay? But the duration is the same. And I can check with the instructions very easily. So just select 32 processes and load the instructions histogram, okay? And if you remember, the one we said before is quite similar. I can do the same, copy and paste the control scale, okay, and they are the similar, okay. So it's the same. Is the chunk between two consecutive calls to the parallel runtime is the same duration, okay. So the final part of my demo is just to compare using the profile of MPI to compare 16 processes with 32. Sorry. What I can do is, let me try to make it smaller. I can paste the size, so they are the same size. And I will have a look on the global statistics. Okay, so instead of having the number of the percentage of time, I can change that to the number of calls. Or number of chunks, number of times that this happens. Okay, so what I see is that the number of the point-to-point communications is almost the same. Okay, while the number of all reduces and the number of computing phases is double when you have less processes. Okay. So basically, well, it's almost double. It's not perfectly double, but it's almost double. Basically, you have the same number of chunks to process. So when you double the number of processes, the number of chunks per process is more or less half of that. Okay? I can compute the average, the total time. Okay? So the total time each process is spent in computation outside MPI is double when you have half of the processes. So it's 10 seconds, I think. It's 10 seconds with 16 processes going down to 5.4 with 32 processes. Okay, the total time in ISEN is not so different because, in fact, the number of, as we have seen, the number of point-to-points you do is the same. Okay. So basically, is when you increase the number, when you double the number of processes, okay, you keep the same amount of communications, and you reduce the computation. You reduce the number of computation, the number of chunks. The duration of the chunks is the same. Okay. Do you have any question? So the idea is, with the tool, I have compared the behavior of the two executions, okay, and I can show a little bit how to play with it. I think the idea is that we can have the break now, and then when we came back, you start working with the tool. First, you will obtain a trace file. I will very briefly explain how to use extraF to obtain the trace file, and then we will do a hands-on where you can start driving the tool. Okay. My recommendation is that for a usage of the tool, you install it locally on your laptop, but in order to minimize the time, I will try to start using the Paraver in Pi from your laptop. Depending on the network requirements, it may be slowed down. If we see that these are really slowed down, then we stop and do the installation on your local machines. All is documented on the slides. Okay? Thank you.